In this work, we present a method for surface normal estimation of tilted images. Estimating surface normal from tilted images is challenging. State-of-the-art methods, including FrameNet, are not applicable to estimate surface normals of tilted images while showing strong performance on upright images. In this example, we show that for two images capturing the relatively similar scene, state-of-the-art network predict accurate surface normal for upright image, with the median of prediction error is of 10 degrees, while the prediction error for tilted surface normal is twice as high. This is mainly caused by the mismatch between the distributions of training and testing data. While surface normal distribution of upright image is well aligned with the training data, there is the distribution gap for the tilted surface normals. Fortunately, there exists a 3D rotation that can reduce this distribution gap. We proposed a spatial rectifier that leverages this 3D rotation to minimize the distribution gap. Given a tilted image, note that there is a small distribution gap with respect to the training data. In addition, we introduced the gravity direction and the principal direction, where the latter is aligned with the y-axis of the image. The 3D geometry shows the orientations of cameras and these vectors with respect to the ground plane. Now we examine the impact of 3D rotations on the surface normal distribution. The rotation is parameterized by the gravity and principal directions. For this rotation, we observe that the distribution gap is minimized. However, at the same time, the image is overly rectified and becomes highly distorted, which we found that this will drastically degrade the network's performance. Hence, we seek for an optimal rotation as the one that balances between minimizing the distribution gap and the pixel loss. Then we obtain the rectification for this image as shown here. Here we show more examples on rectification of other tilted images. In the first example, we observe that the principal direction can also be aligned with the x-axis of the image. In the second example, the rectification uses the rotation in the opposite direction. In the last example, there are 5 dominant directions instead of 3 or 4 as in the previous ones. As shown throughout the example, for each condition of tilted image, we compute the gravity and the principal directions that minimize the distribution gap as well as the pixel loss due to warping. We employ this as ground truth supervision during the training of the spatial rectifier. Before going forward to describe the training pipeline, we first introduce the warping operator. It takes as input an image and the 3D rotation warping parameters, then outputs the warp image. The training pipeline starts first with the tilted image synthesis using the warping operator with the random rotation. Secondly, the synthesized image is warped to the rectified image using the parameters predicted by the spatial rectifier, which we model as a convolutional neural network. Thirdly, a surface normal estimation network, parameterized as a convolutional autoencoder, predicts the rectified normals from the rectified image. Finally, we apply an inverse warping on the rectified surface normal with the parameters from the spatial rectifier to obtain the final output prediction. We supervise our network with the synthesized ground truth surface normals, as well as the gravity and principal direction described in the previous slides. To sum up, there are 3 components of our training pipeline: the tilted image synthesis, the spatial rectifier, and the surface normal estimation on rectified images. During testing, we remove the tilted image synthesis and only use 2 components, the spatial rectifier and the surface normal estimation. We employ the truncated angular loss for training to improve accuracy and robustness of the trained surface normal estimator. In addition, we design a new surface normal estimation network that achieves 2 times speed up as compared to the state-of-the-art, allowing real-time performance. More results about the loss and the network can be found in our paper. To verify the effectiveness of our spatial rectifier, we propose a new dataset called Tilt RGBD that includes both gravity-aligned and tilted images. We compare our proposed network with and without the spatial rectifier and against FrameNet, the state-of-the-art surface normal estimation network, using 2 metrics such as the median of angular error and the percentage of pixels that has error less than 11.25 degree. All networks are trained on ScanNet and tested on Tilt RGBD. Note that in order to evaluate the generalization capability, neither domain adaptation nor fine-tuning is applied. Firstly, thanks to our truncated angular loss, even without the spatial rectifier, our method performs better than the FrameNet on gravity-aligned images. This also applies for tilted images. However, note that there exists a significant performance degradation from gravity-aligned to tilted images. For instance, the FrameNet and our proposed network have the median errors increased by 4 and 2.5 degrees respectively, while the one equipped with the spatial rectifier only increased by 1.5 degree. The same story goes for the other metrics. With the spatial rectifier, our method can greatly improve the performance, especially on tilted images, and achieve state-of-the-art results. Next, we present some qualitative results to demonstrate how our network operates during the inference time. To do so, we show here some intermediate results from the pipeline, such as the rectified image and the rectified surface normals. In this scene, thanks to the truncated angular loss, our estimator can predict highly detailed and accurate surface normals for both the overall structure of the scene and complex objects such as the couch, the pillar, and humans. For tilted images produced by small roll motion, for example in this scene, our spatial rectifier tends to warp them such that the gravity is aligned roughly with the y-axis of the image. However, this is not always the case, especially for images produced by the large roll motion. Take for example, in this instance, our spatial rectifier does not warp the tilted image to obtain a gravity-aligned image, since doing so will highly distort the spatial information of the image. Instead, it transforms the image in such a way that balances the importance between the distribution gap and the pixel loss, which is what we have designs for. As a result, our network is able to produce reliable surface normal estimates in these extreme cases. Here we show some more qualitative results of our method. Next, we show some comparison to highlight the effectiveness of our spatial rectifier in tilted images. As shown previously for gravity-aligned image, both of them produce reliable estimate. However, this doesn't hold true for tilted images. In this case, with some small roll motion, the one without the spatial rectifier produces inaccurate surface normals for most part of the image, especially the floor. The same observation applies to images produced by large pitch motion. Here are more comparison videos. As evident, our method consistently predicts accurate surface normals on our Tilt RGBD dataset that contains a wide variety of challenging scenarios. Our code and dataset are publicly available. Thank you for listening.